Well, you see, if you place your ear close enough to the quiet fabric of the universe, you might hear a faint question echoing back at you. What is the energy that lives in the smallest corners of reality? And why does it behave as though it follows rules written in a language older than stars themselves? I suppose that is where our journey begins tonight, with this curious thing we call quantum energy, a notion that is at once rigorously scientific and somehow profoundly mysterious. When we speak of energy in the world you and I move through, we think of warmth on the skin, light in a room, the gentle pull of gravity as we stand upon the earth. But down there, far beneath the world of touch and sight, energy refuses to flow smoothly. It arrives in little packets, tiny quanta that flicker in and out like thoughts in a drifting mind. And that's the thing. In that microscopic realm, electrons don't glide from place to place. They leap. Photons don't simply shimmer. They carry the imprint of discrete levels of existence. Reality becomes grainy, pixelated, as though the universe itself is whispering that continuity is only an illusion at our scale. Perhaps as we wander deeper into this landscape together, we'll find that the rules governing the smallest particles also shape the stories of stars, of life, of consciousness. And perhaps we will discover that understanding these quanta is, in some quiet way, understanding ourselves. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we first step into the realm of quantum energy, it feels a little like walking into a dimly lit room where every familiar shape has been rearranged. You reach out, expecting the world to behave as it always has, yet the moment your thoughts settle, reality seems to whisper back, not quite what you expected. And that is the quiet wonder of this chapter, the very foundation upon which the quantum world rests. Energy, at the smallest scales, refuses to behave like the continuous stream we sense in the world around us. Instead, it comes in discrete packets, tiny quanta, as if the universe has decided that the microscopic realm should operate to the rhythm of steps rather than a glide. Imagine for a moment the warmth of sunlight on your skin. To you, it arrives as a smooth, uninterrupted glow. But if you were small enough, impossibly small, you would see that the sunlight is built from countless individual particles of energy. Each photon carries a fixed portion of energy, not more, not less. It is as though nature deals its energy like cards in a cosmic game, each with an exact value, no fractions allowed. And that's the thing. Quantum energy is not mystical, though storytellers and daydreamers have long tried to shroud it in the language of miracle. It is simply the way energy behaves at scales where atoms themselves are like cities, and electrons are the citizens darting between quantized homes. I suppose we must linger here a little, letting this truth sink in. Humans have always experienced energy as something fluid. We boil water, we burn fuel, we feel heat rising or falling as if it were some continuous tide. But deep below, in the quiet interior of matter, energy behaves with a strict discreteness. An electron bound to an atom cannot just take any amount of energy it likes. It will only accept specific amounts, like a person who insists on stepping up a staircase rather than sliding along a ramp. It either leaps to the next step or stays where it is, and these leaps are the very essence of the quantum. There is no middle ground, no hesitation mid-air, no gentle stroll from one state to another. Scientists first encountered this unusual behavior with light. They observed that metals emit electrons when struck by light, but not in the way classical physics predicted. If light were a smooth wave, increasing its brightness should always knock more electrons free. But that did not happen. Only light of certain frequencies had the power to liberate electrons, no matter how dim or bright. It was as if light came in individual blows, small packets of energy whose strength depended solely on their frequency. That discovery changed everything. It was the moment humanity realized that energy is quantized, that the universe at its core is built from steps, not streams. You know, the more we sit with this idea, the more it transforms from a scientific oddity into something almost poetic. Because what it implies is that every atom in your body, every particle that dances through you, lives according to a script written in discrete notes. Electrons do not casually drift between energy levels. They move with purpose, absorbing or releasing exactly the amount required for the transition. Nothing more, nothing less. These packets of energy are measurable, predictable, and universal. They form the foundation of all quantum physics, the grammar that underlies the language of the cosmos. And perhaps in a way, this discreteness tells us something about ourselves. We often imagine our lives flowing continuously, one moment dissolving into the next. But when we reflect honestly, we recognize that change comes in jumps. A decision, an insight, a turning point. We leap, just as electrons do, from one state of being to another. Not gradually, not linearly, but in a single breath. It is tempting, of course, to draw metaphors too far, but still, the rhythm feels familiar. Nature seems to enjoy the shape of transition. When we look deeper into this strange quantized world, we find that these energy packets are not merely convenient ideas. They are the only way atoms remain stable. If electrons could take any amount of energy, atoms would collapse or unravel almost instantly. Instead, quantization acts like the supportive framework of a building, preventing electrons from spiraling into the nucleus or escaping without cause. Quantum energy is the quiet scaffolding of existence, invisible to us yet indispensable. Without it, the structure of matter would crumble. Without it, there would be no chemistry, no stars, no life. What fascinates scientists and philosophers alike is how this discreteness emerges from a universe that, at our scale, feels so continuous. Time flows, rivers run, sound waves ripple through the air. Yet beneath these smooth surfaces, everything is made of tiny steps. It is as if the universe is composed of both melody and rhythm, both fluidity and beats, each coexisting without contradiction. And that duality, well, it invites us to think more deeply about the limits of our perception. What else in the cosmos appears continuous only because we are too large, too slow, too bounded by our senses to notice the granularity beneath? Quantum energy also introduced a radical new way of thinking about measurement. To quantify these leaps, scientists had to accept that classical tools and intuitions were no longer enough. The quantum world demanded a new vocabulary, one where probability replaces certainty and where the act of observing itself becomes woven into the fabric of events. Before this shift, we believed energy flowed smoothly, precisely calculable at every moment. But the discovery of quanta urged us to recognize that the universe plays by subtler rules, rules that only reveal themselves when we look at the very smallest things. You see, even the idea that an electron must absorb or emit a precise quantum of energy has profound implications. It means that atoms can only interact with light of specific colors. Each element has its own set of allowed transitions, its own unique signature. If you heat an element and examine the colors of light it emits, you will see bright lines at distinct wavelengths. These spectral lines are not decorative. They are the fingerprints of quantum energy, the proof that nature at its core is quantized. When astronomers look into distant galaxies and analyze the light they see, they too are reading these fingerprints, tracing the behavior of electrons billions of years away. Perhaps it is humbling to realize that even stars must obey the same quantized rules as the tiniest atoms on Earth. Their light, their radiance, their fiery existence all arise from quantum transitions occurring trillions upon trillions of times each second. Fusion, the process that powers the sun, relies on the quantized energies of particles moving within its blazing core. In a very real sense, quantum energy is not a niche phenomenon hidden in laboratories. It is the heartbeat of the universe, setting the tempo for everything from starlight to chemical reactions to the signals pulsing through your nervous system. And that is why I suppose the more we explore, the more quantum energy shifts from a technical term to a kind of cosmic intimacy. Every breath you take is governed by chemistry, and every chemical bond is ultimately shaped by the quantized energies that allow atoms to form molecules. The warmth you feel from a cup of tea, the glow of a lamp on a quiet night, the colors that paint the world around you, all arise because energy is delivered in little packets. Life itself, despite its vast complexity, depends on these tiny transitions. We are, in every sense, creatures of quanta. As we drift further into this landscape of discrete energy, the questions begin to deepen. Why does energy come in packets at all? Why not allow a smooth continuum? Why must the universe take these steps instead of sliding effortlessly between states? These are the kinds of questions that move us from science into philosophy, from facts into contemplation. It is tempting to imagine the universe as a grand design, but perhaps it is simply the most natural way for stability and complexity to coexist. Or perhaps the answer lies in mathematics, in the wave nature of particles, in the strange constraints that arise when matter is both particle and wave. And then, quietly, almost imperceptibly, another thought emerges. If energy is quantized at the smallest scales, what does that mean for space itself? For time? For the structure of reality beyond atoms? You see, this is where the story deepens, where each answer is merely an invitation to step through another doorway. Because once we understand that energy is not continuous, we begin to wonder what else in the universe is built from steps, from discrete notes in a cosmic score, which brings us gently to the next mystery waiting for us. Why energy cannot be continuous inside atoms, and how electrons leap between levels with such surprising elegance. Let us wander there together and see what new wonders unfold when we look more closely at these quantum jumps that shape the universe. Well, you see, once we accept that energy comes in packets, in those tiny quanta that shape the behavior of every atom, a deeper and rather unsettling truth begins to emerge. It is the idea we were just brushing against moments ago, the one that quietly unsettles our classical intuitions. There are no in-between places for energy to hide inside an atom, no gradual slope, no halfway shelf, no gentle ramp for an electron to stroll across. And that is where the strangeness truly begins to unfold, because if energy is quantized, then the architecture of the atom must also be quantized. It must be built from these discrete steps, these allowed levels, as if nature constructed the microscopic world from a series of invisible floors. And electrons? Well, they respect those floors with absolute loyalty. Imagine an electron like a traveler orbiting a great city of forces and fields. In our everyday sense of motion, we would picture it spiraling inward or outward as it gains or loses energy, gliding smoothly through every point along the way. But the quantum world does not permit such gliding. The electron must choose exactly one orbit, one allowed energy state, and remain there. When it moves, it does not drift. It jumps, instantaneously, a leap from one state to another, without ever passing through the infinite number of points that lie between. And that is the thing that catches us off guard, because nothing in the macroscopic world behaves like this. A bird cannot jump from one branch to another without crossing the air in between. A planet cannot hop to a new orbit around its star without traveling through the intervening space. Yet electrons do exactly that, without hesitation, without trace. You might wonder what happens during such a jump. Does the electron vanish from one orbit and reappear in another? Does it smear across space for a fleeting instant? Even today, physicists tread carefully around such questions, because the quantum world is built not on trajectories but on probabilities. The electron is not a tiny marble moving along a track. It is a cloud of possibility, a distribution of where it might be found. And when the transition occurs, that distribution rearranges itself in a blink. The electron is never seen between levels because, quite simply, there is no between to occupy. And whenever such a leap occurs, a tiny messenger of light is born, a photon carrying the exact difference between the two energy levels. No more, no less. A perfect quantum payment for the transition. And if the electron absorbs energy instead, a photon of precisely the right amount must be swallowed. This is the origin of light at the atomic scale. Every color you have ever seen, every line on the spectrum of a star, every glow from a heated gas, arises from these jumps. These silent rearrangements of electrons stepping between discrete levels of energy. It is humbling, I suppose, to realize that the colors of the universe emerge from this strict bookkeeping of energy. Hydrogen emits a series of beautiful lines in the red, blue, and violet regions, forming what astronomers call the Balmer series. Helium, sodium, oxygen, iron, each produce their own distinct set of spectral lines. These are the fingerprints of atoms, the proof that each element has its own internal staircase of energy levels, and each staircase is unique, carved by the architecture of the atomic nucleus and the arrangement of electrons. If you heat a gas or excite it in a laboratory, you will see these lines appear like bright signatures against a dark background. If you look at sunlight dispersed through a prism, you will see dark lines where particular wavelengths have been absorbed by atoms in the sun's outer layers. These lines are the direct imprint of quantum jumps happening across unimaginable distances. And so, well, perhaps now we begin to see why energy cannot be continuous inside atoms. If electrons could occupy any energy they liked, atoms would no longer have these clean, sharp features. Their spectra would blur. Their identities would dissolve. Chemistry as we know it would fall apart, because chemical bonds depend delicately on the organization of electrons in specific states. The periodic table would lose its structure. Stars would not shine with the spectra we observe. The universe would be unrecognizable. But more than that, quantized energy levels prevent electrons from collapsing into the nucleus. Classically, an electron orbiting a nucleus should radiate energy continuously and spiral inward, eventually crashing into the center. Yet atoms are stable. They endure. And the reason is that the lowest energy level, the ground state, is a permitted and bounded place where the electron can remain without radiating energy. It is forbidden from going lower, because no lower level exists. The discreteness of energy saves the atom from an otherwise inevitable collapse. You know, when we sit with this fact long enough, something poetic stirs beneath the mathematics. The universe, at its smallest scales, seems to embrace the idea that stable structures emerge not from continuous freedom, but from quantized constraint. Order arises because only certain energies are allowed. If the universe were smooth at every level, perhaps everything would unravel, constantly radiating, constantly collapsing. But instead, nature chooses steps, and in doing so, it creates architecture, form, identity. Now, consider again the electron's leap. This quantum jump is not simply a curiosity of physics textbooks. It is happening everywhere, constantly, shaping the behavior of materials, the operation of lasers, the colors of nebulae, even the firing of neurons. And each jump releases or absorbs a photon with a specific frequency that matches the energy difference between levels. This is the origin of the spectral fingerprint of each element. It is why neon signs glow red, why sodium lamps cast an amber hue, why oxygen in the upper atmosphere produces green auroras. These colors are not chosen by chance. They are written into the energy structure of atoms themselves. And perhaps this is where another quiet realization appears. Because if every element has its own fingerprint, then analyzing the light from distant galaxies allows us to learn their composition without ever touching them. We read the universe by reading its spectral lines. The atoms in stars millions of light years away speak to us across time and distance, telling us who they are, what temperature they keep, how fast they move. And all of this is possible because electrons cannot take arbitrary energies. They can only leap between their allowed levels, releasing photons with exact quantized colors. You see, this idea that electrons jump rather than glide forces us to rethink movement itself. In the macroscopic world, motion is continuous. But in the quantum world, change is stepwise. An electron's identity at one level is complete and distinct, and at another level equally complete, nothing halfway. It is almost as if the quantum realm asks us to abandon the intuitive view of smooth transformation and instead embrace the idea that nature often prefers suddenness over gradualness. If you think about your own life, you might recognize this rhythm too. We grow gradually, yes, but we change in leaps. A decision, a revelation, a moment of clarity. Perhaps quantum behavior is more familiar to us than we realize, and so this chapter of discontinuity reveals something gently profound. The universe at its smallest scales is not a continuous flow, but a series of carefully arranged possibilities. Energy landscapes are built from steps. Electrons, like dancers in a tightly choreographed performance, leap to precise positions, guided by mathematical rules that allow no improvisation. And the light we see, the colors that paint our world, the radiation that warms the earth, all arise from this extraordinary architecture. When you stare at a flame, each glowing ember is filled with atoms whose electrons are being excited and then falling back to lower states, releasing photons again and again. When you look at the night sky, starlight is the sum of unimaginable numbers of quantum transitions. It is almost poetic to think that the universe glows because electrons refuse to drift smoothly, choosing instead to leap across quantized thresholds, releasing slivers of light as they go. And as we follow this thread further, something else begins to stir beneath the surface. These photons created by quantum jumps, these quanta of light, are not just incidental products. They are the carriers of electromagnetic energy, the quanta that form beams, colors, and information. They reveal that light itself is quantized, that the very concept of illumination depends on this discrete architecture of energy. And so the next chapter waiting for us is not merely about electrons and their steps, but about the photons born from those steps, the quanta of light that travel across the cosmos, embedding the story of quantum transitions into their very frequency. Because once we understand why energy inside atoms is discontinuous, the next natural question arises almost immediately. If electrons create photons when they change levels, then what exactly is a photon? How does it behave? How can light be both a particle and a wave? And how does the color of light emerge from the energy of quantum transitions? Well, perhaps now is the moment to follow that photon outward, to let it lead us from the interior of the atom into the open space beyond, where the strange dual nature of light begins to shine through. And so, with that gentle question glowing at the edge of our thoughts, we step toward the realm of quantum light, ready to explore how photons carry the imprint of every leap made within the atomic world. Well, once we let that tiny photon slip free from the electron's leap, once we allow it to drift outward from the atom that birthed it, we find ourselves following a messenger older than stars. The photon is small beyond imagining, yet it carries with it a story, a precise fragment of energy, the imprint of the difference between two atomic states. And as it travels, it does something rather peculiar. It behaves not only like a particle, a small indivisible packet of energy, but also like a wave, spreading, interfering, rippling across space as though it were made of vibrations rather than substance. This dual nature is one of the great puzzles that ushered humanity into the quantum world. And so, as we stand here, following the photon outward, we must ask, how can something be both a wave and a particle at the same time? Perhaps the easiest way to begin is to imagine a pond. If you toss a pebble into it, waves spread out in perfect circles. Light can behave just like that, dispersing, diffracting, bending around obstacles. But if you place a detector in its path, you will find that the energy arrives in discrete hits, as though the wave has condensed itself into a perfect, indivisible drop. A photon. It is as though nature cannot decide whether to be fluid or firm, whether to travel as a spread-out possibility or as a concentrated impact. And the truth, as quantum physics tells us, is that it is both until we observe it. Before measurement, the photon is a wave of probability, an extended presence describing where it might be found. When we observe it, its nature collapses into a single event, a particle-like interaction. And that's the thing. The world at this scale does not fit into our classical categories. The photon refuses to be pinned down by intuition. Now, what makes a photon different from all other particles is that it has no rest mass at all. It is never still. It cannot be still. It exists only in motion, moving at the cosmic speed limit, the speed of light itself. This lack of rest mass is not merely a curiosity. It is the reason light can travel across the universe unburdened, weaving through the fabric of space-time as effortlessly as a thought passing through the mind. A photon does not age. To a photon, there is no time between its creation and its absorption. It is born and arrives in a single breath of the universe. Yet for us, watching from our slower realm, its journey might span billions of years. And within this tiny quantum traveler lies another astonishing truth. The energy it carries is proportional to its frequency. Higher frequency means higher energy. Lower frequency means lower energy. This means that colors, the ones we see every day, are not mere aesthetic qualities but reflections of energy itself. Red light has less energy. Blue light has more. Violet carries even more still. When you gaze at a rainbow, you are witnessing the energy spectrum of photons, each hue a different rung on the ladder of frequency. But if you look beyond the visible spectrum, you find photons of all energies, from gentle radio waves with enormous wavelengths to fierce gamma rays with frequencies so high they can slice through matter. These are all photons, all quanta of electromagnetic energy, differing only in the amount of energy they carry. It is almost poetic to realize that the entire electromagnetic spectrum is simply a grand, continuous scale of quantum energy levels. Light is not a separate phenomenon. It is simply one band in the cosmic orchestra of frequencies. Now, perhaps the most extraordinary fact is that the sun, our star, is constantly sending a cascade of these quantum packets toward Earth. Each photon that warms your skin on a summer afternoon began its life in the heart of the sun, where nuclear reactions create high-energy photons that bounce around for thousands of years before finally escaping into space. By the time they reach us, they have been scattered, absorbed, re-emitted countless times. But each one that reaches your face is the final remnant of a journey born in fusion. When we say sunlight is a waterfall of quantum energy, we are speaking quite literally. Photons pour toward Earth in unimaginable numbers, carrying the energy that sustains life. Plants catch them. Our eyes detect them. They shape our climate, our weather, our biology. And you know, when you realize that every beam of light is a stream of photons, suddenly the world becomes more intimate. A candle flame is not just glowing, it is releasing a torrent of tiny quanta, each generated by electrons dropping to lower energy levels in heated atoms. A laser is not simply a beam of brightness, it is a disciplined army of photons, all marching in perfect step, all sharing the same frequency, the same phase, the same direction. The glow of your computer screen, the signals in your remote control, the warmth from a fire, even the radio waves carrying voices across continents, all are photons, all manifestations of this same quantum entity. Photons have become the messengers of our modern age, carrying information through fiber optic cables, through airwaves, through space itself. But perhaps the most haunting truth about photons is that they allow us to see the universe not as it is now, but as it was. Because they travel at a finite speed, every photon carries a timestamp in its journey. When you look at the moon, you see it as it was just over a second ago. When you look at distant galaxies, you see them as they were millions or billions of years in the past. Light is a time machine. The night sky is a museum of ancient photons, each one telling a story about where it has come from. In 2025 or any year to come, this truth remains. To gaze into the cosmos is to look backward through time, guided by the photons that have traversed the universe to meet your eyes. Yet for all their elegance, photons reveal another strangeness of the quantum realm. They behave as waves until forced to reveal themselves as particles. They spread out through two slits at once in the famous double-slit experiment, interfering with themselves as though they traverse multiple paths simultaneously. But when a detector watches them, their behavior changes. The interference disappears. The photon chooses a single path. The very act of observation alters the outcome. It is as if photons are aware of being watched, though not in any conscious sense. Rather, the rules of quantum measurement demand that probabilities collapse into definite outcomes when information is extracted from the system. And so, we learn that photons, like electrons, do not behave independently of observation. They behave in relation to it. This dual nature is not limited to laboratory experiments. It is woven into the structure of reality itself. Photosynthesis, the process that sustains nearly all life on Earth, depends on photons being absorbed by chlorophyll molecules, triggering quantum events that initiate the chain reaction of energy conversion. These photons are not simply warming leaves, they are activating electrons, injecting precise amounts of energy into molecular machinery that has been finely tuned by evolution. In this sense, life is not merely sustained by photons, but built upon their quantum nature. When you close your eyes and imagine color, you are recalling the energy of photons that once struck the photoreceptors in your retina. When you wake to a blue sky, your brain interprets photons scattered by air molecules. When a sunset burns red, it is because photons of shorter wavelengths have been scattered away, leaving the lower energy ones to reach your gaze. Every visual experience you have ever known is a conversation between your consciousness and the photons that dance into your eyes. And as we drift deeper into the heart of this chapter, we begin to sense that photons are not just messengers, but fundamental structuring agents of the universe. Without them, atoms would not interact over long distances, chemistry would not occur, life would not emerge. The cosmic microwave background, the afterglow of the Big Bang, is a sea of ancient photons still filling space, whispering the story of the universe's birth. Now, perhaps what is most intriguing is that photons, despite having no mass, exert pressure. Sunlight itself can push. This pressure, though small, can propel spacecraft equipped with solar sails. Imagine navigation powered not by fuel, but by starlight. And indeed, experiments and missions have already demonstrated this possibility. Photons, weightless yet forceful, shape the tails of comets, push dust across interstellar space, and sculpt nebulae over millions of years. But beneath all these wonders lies the simple quantum truth that binds them together. Photons are quanta of the electromagnetic field, energy, electric and magnetic vibrations quantized into individual packets. This is the foundation of quantum electrodynamics, the framework that describes how light and matter interact with astonishing precision. Every time a photon is absorbed or emitted, the rules of this theory orchestrate the process with mathematical elegance. And so, as we stand now at the edge of this chapter, we might find ourselves returning to a question whispered earlier. If photons carry the imprints of atomic transitions, what lies within the atoms themselves? How is energy stored, shaped, and structured inside the nucleus, inside the very heart of matter? Because while photons tell us how atoms communicate with the world, the atoms themselves hold deeper secrets still. Secrets of empty space within their structure. Secrets of nuclear forces binding immense energies. Secrets that speak of the origins of stars and the power that fuels them. And so perhaps the time has come to journey inward once more, to peer into the architecture of the atom itself, where almost all mass resides in an impossibly small nucleus, and where the energies at play dwarf anything electrons or photons alone could reveal. Let us follow the thread of quantum energy deeper into the atomic interior, where space is not what it seems, and where the strength of forces begins to reshape our understanding of the universe. Well, you see, as we follow the photon outward, drifting through space as a tiny messenger of quantum light, there comes a moment when we can no longer resist the pull to turn back and look inward again. because for all the elegance of photons, for all their shimmering dances across the universe, the true heart of energy lies deeper still, inside the atom itself. And perhaps this is where the story becomes even stranger, even more humbling, because the structure we call an atom, the very thing we imagine as solid and foundational, is almost entirely emptiness. I suppose it feels counterintuitive at first. We imagine matter as dense, firm, tangible. But if you were to shrink yourself down to the size of an atomic nucleus, the electrons that define the boundaries of the atom would be unimaginably far away. More than 99.9% of the atom is nothing but space. You could stand inside it and feel as though you were floating in a vast, silent cathedral. The nucleus itself would be a tiny, glowing speck at the center, holding almost all of the atom's mass, a heavy jewel wrapped in a veil of emptiness. And that is the thing. What we consider solid is, at its core, almost entirely void. Yet within that tiny nucleus lies energy so immense that it dwarfs everything we have discussed so far. The forces at play there are not the gentle, probabilistic motions of electrons, nor the drifting photons sliding through space. They are nuclear forces, astonishing in their strength, binding protons and neutrons together with an intensity millions of times greater than chemical energy. This binding force is what makes the nucleus stable, what allows matter to persist, what gives atoms their weight, their identity. Without it, the universe would collapse into a thin mist of particles, unable to coalesce into stars or planets or life. You see, protons are all positively charged, and by classical reasoning, they should repel each other with tremendous force. Imagine trying to push two powerful magnets together, north to north. The resistance is overwhelming. But in the nucleus, protons are squeezed together far more tightly than any magnets you could hold. The electromagnetic repulsion between them is immense, and yet they remain bound. They do not fly apart. They do not explode. Something stronger must be holding them in place. That something is the strong nuclear force, the most powerful known force in nature. It acts only over tiny distances, but within those distances it overwhelms everything else. It binds protons and neutrons into a cohesive whole, creating the nucleus as we know it. And this binding energy, this force that glues the nucleus together, is the source of the immense energy released in nuclear reactions. When the nucleus rearranges itself, when particles inside shift or split or combine, the difference in binding energy emerges as a flood of quantum energy. And perhaps this is where the story becomes almost frightening in scale. Chemical reactions, the ones that warm your skin, power your stove, fuel your body, are tiny compared to what happens in the nucleus. They involve exchanges of electrons, modest shifts in energy. But nuclear reactions tap into the binding forces that hold matter itself together. The energy released in even a single nuclear event can be millions of times greater than that of a chemical bond. It is as if chemical energy is the whisper of the universe, while nuclear energy is its thunder. Consider radioactive decay, the slow transformation of unstable nuclei. When a nucleus is too heavy, too crowded, too unbalanced, it may release particles or radiation to settle into a more stable form. Each such decay releases a burst of quantum energy stored deep within the nucleus. This process powers the heat of Earth's interior, warms the crust beneath our feet, and shapes the geology of our planet. Without radioactive decay, Earth might have cooled long ago, its surface frozen, its continents inert. But the nucleus holds even more dramatic possibilities. When a heavy nucleus splits into two lighter ones, the release of binding energy can be enormous. This is nuclear fission. And when light nuclei combine into heavier ones, the energy released is even greater. This is nuclear fusion. Sparks of fusion fuel the stars. And the sun, our own star, shines because hydrogen nuclei merge into helium in a process that converts mass directly into energy. Einstein's famous equation, relating mass to energy, reveals the sheer potency of this conversion. A tiny amount of mass, just a whisper of substance, becomes a storm of energy. Every photon that reaches Earth from the sun began as one of these. nuclear reactions deep in its core, hydrogen nuclei colliding, merging, releasing energy that begins its long journey outward. The Sun is, in a very real sense, a vast nuclear furnace, operating entirely through the principles of quantum mechanics. Quantum tunneling allows hydrogen nuclei to overcome their mutual repulsion and fuse, even when classical physics would say it is impossible. Without this quantum effect, the sun would not shine. The warmth we feel on our faces, the light that illuminates our days, the energy that sustains life on Earth, all of it is born from quantum processes in the atomic nucleus. And perhaps this is where we pause again, letting the weight of that revelation settle. The energy inside the nucleus is not merely theoretical. It shapes the cosmos, it powers the stars, it fuels the evolution of galaxies. Even in the vast emptiness between stars, the nuclear physics of the early universe determined how matter clumped together, how elements formed, how cosmic structures emerged. Yet the nucleus itself remains almost unfathomably small. If the atom were enlarged to the size of a stadium, the nucleus would be a tiny grain of sand at the center. And yet this grain carries nearly all the weight. It is dense beyond human comprehension, containing protons and neutrons packed tightly together. A teaspoon of pure nuclear matter, if such a thing could exist outside a neutron star, would weigh billions of tons. It is humbling, almost unsettling to realize that the solidity of everything we touch stems from forces hidden inside objects far too small for us to see. And still, for all its density and power, the nucleus is not immutable. Its internal structure can be disrupted or rearranged, and when this occurs, quantum energy is released in extraordinary amounts. This is why nuclear reactions have such potential, both constructive and destructive. They tap into the deepest layers of matter, the very foundations of existence. Even the stars themselves will one day exhaust their nuclear fuel, collapsing, exploding, transforming into new cosmic forms. I suppose there is something almost poetic about that. The same forces that grant stability to the universe's smallest building blocks also orchestrate the grandest cycles of birth and death among the stars. From the nucleus to the cosmos, the patterns echo one another. Energy stored in the smallest places shapes the largest structures. And perhaps we might reflect on how strange it is that this immense energy resides within objects we encounter every day. A grain of sand, a leaf, a glass of water. Every atom contains a nucleus charged with unimaginable strength, yet we live oblivious to it. The world feels stable precisely because this energy remains locked away, held tight by the strong nuclear force. Only under special circumstances, deep in stars, in reactors, or in rare natural processes, does this energy become visible. But even as we marvel at the nucleus, questions begin to arise. If matter is mostly empty space, why does it feel solid? Why do we perceive a world of firmness and resistance? The answer lies partly in the electromagnetic interactions between electrons and nuclei, but partly in the quantum fields that give particles their mass. And when we look closer at the nucleus, we find not only protons and neutrons, but also the quantum fields that bind them, that flicker and shift in ways still not fully understood. And so, once again, we reach the edge of our certainty. The nucleus answers many questions, but it also opens doors to deeper mysteries. Why does the strong force behave the way it does? What lies inside protons and neutrons themselves? How do the quantum fluctuations within the nucleus contribute to its stability? These questions lead us toward the next realm of our journey, where quantum effects grow even stranger. Because before we can explore the limits of matter, before we can examine the boundary between stability and transformation, we must turn to the phenomena that defy our classical intuition most directly. Phenomena that allow particles to move through barriers, to exist in multiple states, to remain connected across vast distances. And so perhaps now, having wandered through the immense energies locked within the nucleus, we are ready to explore the curious behaviors that arise when quantum rules are pushed even further. Behaviors that reveal just how different the microscopic world is from the macroscopic reality we experience. let us step gently toward those strange quantum effects, the ones that blur the line between possibility and impossibility, and see what they have to tell us about the nature of the universe. Well, you see, once we emerge from the depths of the atomic nucleus, still carrying the quiet astonishment of the immense energies bound in that tiny kernel of matter, something else begins to shimmer at the edges of our curiosity. It is as though the universe, having shown us its strength, now wishes to reveal its strangeness. And this strangeness is subtle at first, like a whisper against the ear, a soft suggestion that the rules we take for granted are not quite as firm as they appear. Because in the quantum world, particles do things that no object in our everyday experience could ever dream of doing. They slip through walls. They exist in multiple states at once. They remain connected across vast distances in ways that defy classical reasoning. And, that's the thing. The universe seems to enjoy bending, stretching, and sometimes completely overturning the boundaries of our intuition. Perhaps the best way to approach this is simply to start with one of the most astonishing quantum behaviors, one that sounds almost like a fairy tale when first encountered. A particle can pass through a barrier it has no energy to overcome. This is quantum tunneling. Imagine you are standing before a hill too tall to climb. Classical physics would say that unless you have enough energy to climb over, you will never reach the other side. And yet, in the quantum realm, particles do not live by such strict rules. They behave like waves, and a wave does not stop abruptly at a barrier. It fades, continues, and sometimes reappears on the other side. So an electron confronting a barrier will sometimes simply appear beyond it, as though reality offers it secret passageways. It does not smash through. It does not break the barrier. It simply tunnels. And this tunneling is not a rare curiosity. It is essential to the workings of stars. Without tunneling, hydrogen nuclei in the sun would never fuse because they do not have enough classical energy to overcome their mutual repulsion. Quantum mechanics steps in, allowing them to slip through the energetic barrier and ignite the fusion that lights the cosmos. In that sense, the sun shines because the universe is stranger than we once believed. But tunneling is only the beginning. There is another phenomenon, even more unsettling, that makes us question what it means for something to be in a particular state. We call it superposition. And to appreciate it, you must first set aside the idea that a thing must be one way or another. In the everyday world, a coin is either heads or tails. A door is either open or closed. But in the quantum world, a particle can exist in multiple states simultaneously. It is not indecisive. It is not oscillating between options. It is genuinely occupying all possible states until we measure it, until we force the universe to choose. And only in that moment does one outcome become real. Until then, the particle exists as a cloud of possibilities, a blend of what could be rather than what is. Superposition is not just theoretical. It is the foundation of quantum computing, of interference experiments, of the delicate operations that hint at the tremendous potential of future technologies. And yet, beneath all of that, superposition challenges us to rethink our relationship with reality. What does it mean for something to be real if it occupies many possibilities at once? What does it mean for us as observers to collapse those possibilities into a single outcome? As I reflect on it, I often feel the universe is inviting us to consider that certainty is a luxury of the macroscopic world, not a fundamental truth. And then we arrive at quantum entanglement, perhaps the most enigmatic of all quantum effects. Einstein famously called it spooky action at a distance, because it seems to defy everything classical physics claims about how information should behave. Two particles can become entangled so that their states are linked. Measure one, and the other instantly reflects that measurement, no matter the distance separating them. They could be on opposite sides of the universe, and yet their connection persists beyond any classical explanation. It is not that one sends a signal to the other. Rather, they share a single quantum state, a unity that transcends spatial separation. They are, in a sense, one system stretched across space. This phenomenon is not merely philosophical. It is the backbone of emerging technologies like quantum cryptography and quantum networks. It suggests that information may be woven into the fabric of reality in ways we do not yet fully grasp. And perhaps, as we sit with this idea, we begin to sense that the universe is less a collection of isolated objects and more a tapestry of relationships bound together by quantum threads. But there is something else, something subtler and more unsettling still, that arises when we consider these phenomena together. It is the role of the observer. In classical physics, measurement simply reveals what is already there. A thermometer reads the temperature. A scale measures weight. But in quantum physics, measurement does not merely reveal, it affects. Observing a system changes it, collapses superpositions, alters probabilities, forces the particles involved to decide which state to adopt. The act of looking becomes part of the physical process. We are not distant spectators standing outside the play. We are participants. And, this leads us into one of the most debated and misunderstood features of quantum mechanics, the observer effect. Not consciousness in the mystical sense, but interaction in the physical sense. To measure something, you must disturb it. To observe a photon, you must hit it with another photon or influence it in some way. The universe does not give up its secrets gently. Our attempts to peer into the quantum realm always ripple through the system, reshaping the very thing we wish to study. Perhaps the most astonishing part of all this is that these strange quantum behaviors are not rare or exotic. They are everywhere. They govern the atoms in your body, the chemical reactions that fuel your cells, the processes that shape materials, electronics, even the operation of the sun. The world we experience every day emerges from this underlying strangeness, from particles tunneling, superposing, entangling, and responding to observation. And yet, because these effects cancel out at larger scales, we go through life unaware of the bizarre choreography beneath our feet. I suppose it is humbling, and maybe even a bit poetic, to realize that reality is built from phenomena we cannot see, but that somehow shape every experience we have. It invites us to question the solidity of the world, the boundaries between object and observer, the nature of cause and effect. It invites us to reconsider what we mean by certainty. And if we look closely enough, another pattern begins to appear. The strange behaviors we observe in quantum mechanics do not arise from chaos. They arise from rules, precise, consistent, deeply mathematical rules that govern the microscopic structure of the universe. The unpredictability we sense is not randomness, but a reflection of probabilities, woven into the fabric of reality itself. In this sense, quantum mechanics does not diminish the beauty of the universe. It enhances it. It shows us that uncertainty and possibility are not flaws, but features, necessary ingredients in the creation of complexity, stability, and life. Now, as we drift gently toward the end of this chapter, letting these strange quantum effects echo in our thoughts, we might notice something else tugging quietly at our curiosity. Because if particles can behave in such extraordinary ways, slipping through barriers, existing in overlapping states, connecting across vast distances, then what happens in the empty spaces between them? What is the nature of the vacuum that lies beneath matter, beneath fields, beneath space-time itself? You see, the next mystery waiting for us is not about particles at all, but about the space they inhabit. The vacuum, as we once imagined it, is not truly empty. It is alive with fluctuations, energy, and ephemeral particles that appear and vanish. Even nothingness is not nothing. And perhaps now, with our minds tuned to the strange rhythms of the quantum world, we are ready to explore the restless ocean of energy that lies beneath everything, the zero-point energy that vibrates at the foundation of the universe. Well, you see, after wandering through this strange landscape where particles tunnel through barriers and stretch themselves across possibilities, where entangled partners whisper across cosmic distances, we arrive at a place even more unsettling, yet oddly serene. It is the vacuum, the void, the place we once imagined as absolute nothingness. And perhaps this is the greatest twist the universe offers us, the quietest revelation. Nothingness is not empty. The vacuum, far from being a barren stage upon which matter performs, is itself alive with restless motion. And if we look closely enough, with instruments sensitive enough and minds open enough, we find that the vacuum is humming with energy, even at its lowest possible state. This is what physicists call zero-point energy, the shimmering backdrop of quantum fluctuations that exists even when all classical energy has been drained away. And I suppose it begins with the simple yet profound idea that in the quantum world, motion never fully stops. Particles cannot rest completely. Fields cannot settle into absolute stillness. Even at the point where classical physics insists energy should vanish, something remains. A faint vibration, a whisper of uncertainty, a reminder that the universe, at its foundation, refuses to be perfectly quiet. Imagine, if you will, a guitar string stretched tight across a frame. In classical thinking, you could dampen it entirely until it produces no sound. But in quantum terms, even when silenced, the string would still quiver ever so slightly, a fluctuation born from the uncertainty principle. Something always persists. Motion cannot be reduced to zero, and so it is with the vacuum. It cannot sit still. It cannot flatten itself into pristine emptiness. There is always some residual trembling, some baseline energy that cannot be removed. And that leads us to the startling conclusion that the vacuum is not truly empty. It is filled with these tiny fluctuations, appearing and vanishing, borrowing energy from the universe for brief moments before returning it without leaving a lasting trace. These fluctuations manifest as virtual particles, ephemeral guests that pop into existence and disappear, each event so fleeting that it seems more like a suggestion than an actual happening. But in the collective, these quantum tremors shape the behavior of the universe. They exert forces. They shift energy levels. They influence matter in subtle but measurable ways. Perhaps the most famous example is the Casimir effect, where two metal plates placed close together experience a force pulling them inward, not because of any classical attraction, but because the vacuum fluctuations between the plates differ from those outside. Space itself is pushing on them. The vacuum is alive, exerting pressure. That is a deeply unsettling idea if you let it settle in your mind. The void has weight, influence, texture, and the more we explore this restless vacuum, the stranger it becomes. Because these quantum fluctuations are not occasional accidents. They are continuous, spontaneous, persistent, everywhere in space, from the gaps between electrons and nuclei to the vast emptiness between galaxies. The vacuum seethes. It is a continual dance of creation and annihilation, of fields rising and falling, of particles blinking into being. The vacuum is not the absence of energy, but the lowest energy state available. And even at that lowest level, the value is not zero. Perhaps this is the point where the boundary between physics and philosophy begins to blur. Because when we imagine the universe before matter condensed, before stars ignited, before structure emerged, what existed? If vacuum energy is always present, then even in the earliest moments, before the first particles formed, the universe was humming with zero-point energy. And many cosmologists believe that this energy played a role in the expansion of the cosmos, driving inflation, shaping the large-scale structure we now observe. But what fascinates me most is how this restless vacuum touches everything. Even the stability of atoms depends on zero-point energy. Electrons do not collapse into nuclei, partly because the quantum fields that define their behavior are never completely still. The ground state of the electron in a hydrogen atom is not motionless, but constantly fluctuating, guided by the wave function's delicate probabilistic dance. Remove those fluctuations, and the atom would collapse. Matter itself would not exist. And there's something poetic about that, I suppose. That existence depends not on solidity, but on vibration, on the quiet insistence of quantum fields that they cannot, will not settle into absolute stillness. Life, stars, galaxies, even time as we experience it, all emerge from a universe that refuses to be silent at its most fundamental level. You see, even the idea that particles appear and vanish might sound like speculation or metaphor, but it has real consequences. Virtual particles shift the energy levels of atoms, modify electromagnetic forces, and even play a role in phenomena like Hawking radiation near black holes. A black hole is not perfectly black. It glows, ever so faintly, because the fluctuations at its event horizon produce particles that sometimes escape before they are swallowed. The vacuum itself leaks energy from the boundary of a black hole. The void becomes luminous, and if we follow this idea further, something even more astonishing begins to surface. The vacuum might hold immense amounts of energy, far more than we currently understand, far more than we know how to harness or even fully describe. Some estimates suggest that if we could extract even a fraction of the zero-point energy in a single cubic centimeter of space, it would exceed the energy output of the sun. That is, of course, a theoretical statement. We do not know how to access such energy. But the idea that space itself contains vast reserves of hidden power is not fantasy. It is a consequence of quantum field theory. Perhaps in a distant future, not in 2025, but in centuries or millennia beyond, humanity may learn to manipulate vacuum energy. But for now, it remains a reminder of how little we truly understand. The universe is giving us hints, fragments of truth, glimpses into its underlying mechanisms. Yet the deeper we look, the more mysterious it becomes. And still, the restless vacuum carries an even subtler implication. If fluctuations are constant, if particles are continually emerging and disappearing, then the vacuum is never truly at rest. Time itself, at the quantum scale, becomes inseparable from these fluctuations. Energy and time are bound together by an uncertainty principle. The shorter the moment you examine, the less defined energy becomes. This allows fluctuations to appear. It suggests that time, at very small scales, behaves differently than we experience in our macroscopic world. In this sense, zero-point energy becomes a bridge to an even greater mystery. Because if the vacuum holds energy, and if that energy fluctuates, then perhaps time does as well. Perhaps time is not a smooth flow, but a jittering sequence of possibilities at microscopic scales. Perhaps what we perceive as continuity is built from fluctuations too rapid for us to detect. The universe might not simply exist, it might be continuously reassembling itself at every moment. You know, there is something deeply humbling in that thought. We live in a world that feels stable, steady, predictable, but beneath that stability lies a churning ocean of uncertainty, a sea of quantum motion that sustains existence in ways we are only beginning to understand. And the vacuum, instead of being a void, becomes the foundation of creation, the canvas upon which reality paints itself. Yet as we rest our thoughts here for a moment, letting these ideas ripple through the mind, another question begins to emerge. If the vacuum is filled with energy, if fluctuations are constant, and if the uncertainty principle binds energy to time, then what exactly is the relationship between quantum energy and time itself? How does time behave in the quantum world? Does it tick? Does it vibrate? Does it fluctuate? And perhaps, well, this is where the next chapter naturally rises before us. Because zero-point energy invites us to consider that energy and time are intertwined in ways that stretch beyond classical reasoning. To understand why fluctuations happen, why energy cannot reach zero, why particles borrow existence from the vacuum, we must explore the quantum connection between energy and time, where uncertainty reigns and where the flow of time looks very different from the orderly progression we feel in our everyday lives. So let us step quietly now from the trembling vacuum into the delicate fabric of time itself, where quantum rules reshape our understanding of past, present, and possibility. Well, you see, once we recognize that the vacuum itself trembles with energy, never fully still, never truly silent, a new and rather haunting question begins to rise. If energy can never quite reach zero, if fluctuations shimmer even in the quietest corners of the universe, then what does that mean for time? Not time as we feel it in our bones, with mornings and evenings and the slow weathering of memory, but time as it exists in the microscopic domain, where particles flicker in and out of being, where existence is less a steady line and more a restless vibration. And that is the thing. The closer we drift toward the quantum world, the more time begins to lose the familiar shape we carry within us. You see, in classical physics, time is a clean arrow, a smooth flow that we can divide into seconds, minutes, years. Energy, too, is precise and well-defined. But in quantum mechanics, energy and time are linked by an uncertainty principle that refuses to let both be known with perfect clarity. If you try to pin down the energy of a system exactly, the duration of that state becomes foggy. If you attempt to measure a moment in time with infinite precision, the energy within that moment becomes uncertain, widening into a cloud of possibilities. It is as if the more tightly you grasp time, the more energy slips through your fingers, and the more precisely you measure energy, the more time dissolves into haze. Perhaps what this tells us is that time at the quantum scale is not rigid. It is elastic, trembling, shaped by the same fluctuations that animate the vacuum. And this elasticity is not some abstract mathematical curiosity. It is woven into the events that shape reality. Because particles can borrow energy from the vacuum for exceedingly short periods, existing briefly in states forbidden by classical rules. They do this without violating conservation laws, because the uncertainty principle allows such borrowing, provided the loan is repaid swiftly. The shorter the time window, the more energy may be borrowed. For the briefest trembling of existence, particles may appear, interact, influence one another, and then vanish, restoring the cosmic balance. This fleeting interplay is one of the quiet miracles of quantum mechanics. It is the foundation of quantum fluctuations, those momentary disturbances in fields that ripple through the vacuum. These fluctuations are not rare. They are continuous, restless, ever-present. They ensure that space is never calm, and the energy they produce is permitted by the uncertainty that ties energy and time together. The vacuum boils, not with matter in the classical sense, but with these possibilities, these half-formed events that arise, fade, arise again. And perhaps, as we sit with this idea a little longer, we begin to sense a deeper truth whispering beneath the mathematics. The flow of time at the quantum scale is not the time we know. It does not march forward with steady cadence. It behaves more like a foam, a seething structure, with fluctuations too rapid and subtle for us to perceive directly. Our perception of time, the macroscopic river in which we live our lives, emerges from countless microscopic vibrations, each shaped by uncertainty, each stitched together into the continuity we experience. It may even suggest that time and energy are not separate categories at all, but two faces of a deeper unity. Change requires energy. Energy requires time. And at the quantum scale, this exchange is negotiated not with precision, but with permission. A particle may borrow energy because the briefness of its existence makes the uncertainty tolerable. The vacuum allows such brief transgressions. It offers tiny windows where classical rules soften, where the universe accepts that momentary imbalances must occur for reality to sustain itself. And, as strange as it sounds, this borrowing is vital. Without these fluctuations, atoms would be unstable. Forces would not behave as they do. Even the structure of the universe, the way galaxies cluster, the way cosmic expansion unfolds, may be influenced by the restless interplay of energy and time. The uncertainty principle is not a limitation. It is a creative engine, generating possibilities where classical physics sees none. Yet the more deeply we peer into this relationship between time and energy, the more blurred the boundary between past and future becomes. At extremely small scales, time may not behave as a smooth continuum. It may jitter, leap, oscillate. And this might help explain why certain quantum processes seem to defy temporal expectations. Particles can tunnel through barriers as though borrowing energy for a short moment. Virtual particles appear and disappear, Interactions occur that depend not on a fixed sequence of events, but on overlapping possibilities. In this view, time becomes less a dimension we traverse and more a fluctuating landscape shaped by quantum rules. Just as energy comes in quanta, perhaps time itself has a granularity, a small-scale structure we cannot currently perceive. At macroscopic scales, these quantum jitters blur together into the continuous flow we recognize, much like individual water droplets merge into the smooth stream of a river. But beneath that appearance, the river is turbulent with motion. Perhaps the most fascinating part of this is realizing that the universe allows temporary violations of what we consider sacred laws, provided they occur within the constraints of the uncertainty principle. Particles that borrow energy briefly are like visitors stepping into existence on borrowed time. These events contribute to the physical behavior of fields, influence electromagnetic forces, and help define the stability of matter. They are, in a sense, the invisible scaffolding upon which reality builds itself. And yet, well, the deeper we explore, the more the question of time refuses to settle. What does it mean for a process to occur if the timing of its occurrence cannot be sharply defined? What does it mean for energy to fluctuate if time itself is part of that fluctuation? The classical view of time as a rigid frame begins to crumble under the pressure of these quantum truths. Time becomes dynamic, mutable, infused with probability. There is something almost philosophical in that. We tend to anchor our lives in the notion that time moves forward, leaving the past behind us and carrying us toward an uncertain future. But in the quantum world, that boundary between past and future is not as clear. Processes may depend on states that exist simultaneously. Fluctuations may arise with no classical cause. The universe seems comfortable with ambiguity in places where we are not. And yet, for all this strangeness, the macroscopic world remains stable. We can measure time. We can rely on clocks. We can live our lives without worrying that the flow of time will suddenly dissolve beneath our feet. The apparent stability of time emerges from countless quantum fluctuations smoothing into an average experience. And in a poetic sense, this reminds us that the certainty we cling to is an emergent property, not a fundamental truth. Now, as we approach the boundary of this chapter, another realization begins to shimmer into view. If energy and time are bound by uncertainty, if fluctuations permeate the vacuum, if particles may borrow existence from brief moments, then how does this relate to our classical understanding of motion, position, and momentum? Why do the large-scale rules we rely on begin to fail when we peer too closely into the quantum structure of reality? You see, the next mystery waiting for us lies in the comparison between the quantum world and the world shaped by Newton's classical laws. To understand why energy is discontinuous, why time flickers, why particles behave probabilistically, we must examine how quantum energy diverges from classical expectations. And perhaps now, having wandered through the fluctuating interplay between energy and time, we are ready to explore that contrast. So let us move gently into that next landscape, where classical continuity gives way to quantum discreteness, where certainty gives way to probability, and where the rules that govern the macroscopic world are revealed to be only approximations of the deeper quantum truth beneath them. Well, you see, as we drift from that trembling boundary where energy and time blur together, something quietly profound begins to dawn on us. If the quantum world behaves with such fluid uncertainty, with fluctuations and leaps and probabilities, then why does the world we move through each day feel so stable, so continuous, so obedient to the old rules of Newton? Why does a ball thrown into the air follow a smooth arc? Why does a chair remain solid beneath us? Why does time feel like a river instead of a jittering foam? And that's the thing. The laws of classical physics are not wrong, but they are incomplete. They emerge from the quantum rules the way a melody emerges from individual notes. From afar it sounds smooth, but up close it is built from countless discrete vibrations. Perhaps the best place to begin is with motion itself. Newtonian physics imagines a world that can be described with perfect precision. If you know the position and momentum of an object, you can predict its future indefinitely. In that classical picture, energy is continuous, flowing smoothly from one form to another. A particle can have any amount of energy, any position, any momentum, any velocity, but the quantum world refuses such tidy simplicity. It insists on uncertainty. You cannot know both position and momentum with infinite accuracy. You cannot pin down energy and time simultaneously. You cannot demand continuity where nature has woven discreteness into the fabric of reality. The discontinuity of quantum energy is one of the most striking departures from classical thinking. In Newton's world, a planet can orbit at any distance. A pendulum can swing with any energy. But in the quantum realm, electrons can occupy only specific energy levels. They do not slide smoothly from one orbit to another. They leap. Energy is not a flowing stream but a staircase. And we, looking at the world from our macroscopic perspective, tend to overlook these small steps because they are too tiny, too rapid, too subtle for our senses to detect. But the universe does not overlook them. They shape the entire structure of matter. And perhaps here we might pause and let ourselves marvel at the fact that classical continuity is an illusion born of scale. If we were small enough to sit inside an atom, we would see electrons jumping, disappearing, reappearing, existing as probability clouds rather than precise points. We would see energy levels like layered shelves, each separated by quantized steps. But because our bodies, our senses, our world are made of countless atoms acting together, these steps blend into smoothness. 1,000 tiny discontinuities become a single continuous experience, the same way the individual frames of a film merge into seamless motion when projected quickly enough. Another profound difference emerges in how the two worlds treat certainty. Classical physics is deterministic. If you know enough, you can predict everything. But quantum mechanics replaces determinism with probability. Even if you know the wave function of a particle perfectly, you can only predict the likelihood of finding it in a certain place, not its exact position. The universe at small scales does not commit to a single story until a measurement forces it to choose. And the moment of measurement itself changes the system. The observer becomes entangled with the observed. The act of looking reshapes the landscape. Classical physics assumes that measurement merely reveals reality. Quantum mechanics shows that measurement creates reality at the moment of observation. Perhaps that sounds unsettling, but when you step back, it becomes strangely beautiful. It suggests that the universe, at its deepest level, is not a rigid machine, but a conversation, a dialogue between possibility and observation, between potential and manifestation. This leads us naturally to the question of continuity. In Newton's world, energy, position, and momentum vary smoothly. But in quantum mechanics, not only is energy quantized, but the very notion of a precise trajectory dissolves. Particles do not have well-defined paths between 2 points. They explore all possible routes simultaneously, interfering with themselves, shaping probabilities. A classical path is not a fundamental truth, but an approximation that emerges when many particles act together over scales large enough that quantum interference becomes negligible. I suppose this helps explain why the macroscopic world feels so predictably Newtonian. The quantum uncertainties wash out when billions upon billions of particles interact. Their individual uncertainties average into stability. Their probabilities converge into certainties. Their discontinuous jumps blur into continuous motion. And so the classical world emerges not as the foundation, but as the shadow of the quantum world, a coarse-grained version of deeper truths. One of the most elegant demonstrations of this contrast lies in the inability to measure position and momentum simultaneously with perfect accuracy. In classical mechanics, there is no such limitation, but the quantum world imposes a fundamental constraint. The more precisely you know one quantity, the less precisely you know the other. This is not a limitation of instruments. It is not an engineering problem. It is a property of nature itself. At the quantum scale, particles do not possess exact positions and momenta simultaneously. They are described by wave functions that encode a spectrum of possibilities. This uncertainty is not merely an abstract rule. It shapes physical systems. Electrons and atoms cannot spiral into the nucleus because confining them to an infinitesimally small space would make their momentum uncertain to an enormous degree, raising their energy. The stability of matter arises from quantum uncertainty. In a poetic sense, atoms persist because particles refuse to be pinned down too sharply. A universe built on perfect certainty would collapse. A universe built on uncertainty thrives. Even more striking is the way quantum mechanics treats empty space. In classical physics, a vacuum is truly empty, but quantum mechanics insists that empty space is filled with fluctuating fields. These fields give rise to virtual particles that influence the behavior of real particles. They shift energy levels, exert forces, alter dynamics. Classical physics ignores this restless undercurrent because it is invisible at macroscopic scales, but at microscopic scales it becomes essential. The classical vacuum is silent. The quantum vacuum is alive. And this divergence between old and new pictures leads us to another key insight. The quantum world is statistical. Its predictions come in terms of probabilities. But when aggregated over many events, these probabilities become the deterministic laws we recognize in daily life. So perhaps determinism is not a fundamental property of reality but an emergent phenomenon, like a crowd's movement emerging from the unpredictable motions of individuals. Consider heat. At the microscopic scale, temperature is the motion of molecules, random and chaotic. But at the macroscopic scale, heat becomes smooth, predictable, classical. Temperature is a statistical reality, not a microscopic one. So too with many classical laws. They arise from the smoothing of quantum irregularities. And perhaps this is why classical physics feels so right to us. Our senses evolved in a world where quantum effects cancel, where the smoothness of probability distributions becomes indistinguishable from certainty. Our intuition is tuned to scale, not to fundamental truth. And that intuition, though deeply useful, becomes misleading when we peer too closely into the quantum world. Still, for all their differences, classical and quantum physics are not enemies. Classical physics is a remarkable approximation of quantum mechanics when applied to large systems. It works beautifully in nearly every situation we encounter in daily life. In that sense, classical physics is not wrong. It is a simplified reflection of deeper patterns. And quantum physics does not destroy classical intuition. It extends it, enriches it, reveals the underlying mechanisms that give rise to the stable world we inhabit. And perhaps here, as we linger between the macroscopic and microscopic realms, a new question begins to rise. If quantum mechanics underlies the classical world, and if quantum effects govern not only particles but also energy, time, and the vacuum itself, then how do these quantum principles shape the technologies, tools, and scientific breakthroughs that define our age? How does this strange physics translate into practical applications, into machines that diagnose disease, into lasers that guide airplanes, into solar cells that harvest sunlight? Because the next landscape in our journey is not philosophical, but profoundly practical. It is where quantum energy steps out of the abstract and into the devices we touch, the systems we build, the innovations shaping the future. It is where the strange behaviors of particles become the engines of technology. So now, with the contrast between classical and quantum worlds shimmering clearly in view, let us step forward into the realm of real-world applications, where quantum energy becomes not only a mystery, but a tool, a resource, a transformative force guiding the next chapters of human creativity. Well, you see, once we recognize how classical certainty dissolves into the swirling probability landscape of the quantum world, it becomes almost impossible not to wonder how humanity has learned to tame such strangeness. We do not simply observe quantum energy from afar, we shape it, bend it, harness it, and somehow, through centuries of curiosity and experiment, we have woven quantum rules into the machinery of modern life. It is almost poetic, really. The same quantum leaps inside atoms, the same tunneling beneath energy barriers, the same strange dualities of photons, now pulse through the technologies that power our civilization. And that's the thing. Quantum energy is not merely a theoretical curiosity. It is a practical force, one that illuminates our world, reveals our bodies, measures our time, and may soon transform the very architecture of computation itself. Perhaps the most relatable example of quantum principles shaping our daily lives is the solar cell. It sits quietly on rooftops and spacecraft, gathering sunlight as if performing a simple act of absorption. But beneath its smooth surface lies a quantum drama. When a photon strikes a semiconductor, it carries with it a precise packet of energy. If this energy matches the band gap of the material, it excites an electron, lifting it into a higher energy state and leaving behind a hole. This leap, this quantized transition, is the heart of the photovoltaic effect. Sunlight becomes electricity not by magic, but by electrons obeying quantum rules and jumping across energy levels with elegant precision. Without quantization, solar cells would not function. Without the discrete nature of photon energy, the world could not harvest sunlight so effectively. And perhaps that idea alone should make us pause. The sunlight falling on your skin, the warm glow, through your window, the gentle hum of a solar-powered generator, all are powered by quantum jumps tiny enough to fit inside the architecture of a single atom. It is humbling to realize that the renewable technologies shaping the future depend on quantum mechanics functioning exactly as it does, without fail, in every instant. But sunlight is only one way we use quantum energy. Consider the MRI machine, that enormous humming cathedral of magnetism that allows doctors to see inside the human body without ever making a single incision. What it detects is quantum spin, a deeply quantum property of particles like protons. Spin is not a literal spinning motion, but a fundamental quantum characteristic, one that aligns itself with magnetic fields. When placed inside a powerful magnetic field, the spins of hydrogen nuclei align. Radio waves then nudge these spins out of alignment, and as they relax back, they emit signals that reveal the structure of tissues in exquisite detail. The clarity of an MRI image is not a triumph of classical physics, but of quantum mechanics whispering from within your atoms, guiding protons as they resonate with unseen energy patterns. It is remarkable to think that our bodies bloom with quantum signals. Every drop of water in you contains hydrogen atoms with spins ready to speak, ready to reveal the architecture of organs and tissues through their quantum resonance. The MRI scanner simply listens, translating these whispers into images that save lives. A quantum conversation unfolding inside hospitals every day. And then, of course, there is the laser, one of the most elegant manifestations of quantum behavior. A laser does not emit just any light. It produces a beam of photons that are identical in frequency, direction, and phase. This extraordinary coherence arises from stimulated emission, a process predicted by Einstein in which an excited atom, nudged by an incoming photon, releases a second photon with precisely the same properties. The atom's quantum energy level collapses, releasing its stored energy in perfect harmony with the incoming photon. One photon becomes two become four, and a cascade unfolds until a brilliant, coherent beam emerges. Every barcode scanner, every fiber optic cable, every precision measurement tool, every surgical laser operates because atoms obey these quantized rules, because photons can march in perfect lockstep when coaxed by the right energy conditions. Light becomes not just illumination, but precision, direction, intention. And at the heart of it lies a single quantum transition, repeated millions upon millions of times. Speaking of precision, perhaps nothing embodies quantum influence on technology more profoundly than the atomic clock. These clocks do not measure time using gears or pendulums or springs. They measure the frequency of quantum transitions inside atoms, often cesium or rubidium. An electron in a specific energy level oscillates at a frequency so stable, so exquisitely reliable that it becomes the heartbeat of global timekeeping. The accuracy of an atomic clock is astonishing. It may drift by less than a second over millions of years. And the reason is purely quantum. Electrons can only transition between discrete states, emitting or absorbing photons with precise energies. Those energies define frequencies that do not change. the universe itself becomes the metronome, guiding our measurement of time. Without atomic clocks, GPS would be impossible, telecommunications would falter, scientific experiments requiring extreme precision would collapse into noise. Even the smooth functioning of global finance relies, in some subtle way, on the unwavering rhythm of quantum transitions deep inside atomic clocks, ticking quietly in laboratories and satellites. And yet, as astonishing as these technologies are, they are only the beginning. The quantum revolution is not a past achievement, but a wave still cresting, carrying with it the promise of machines that compute not in bits, but in quantum states. Quantum computers exploit superposition and entanglement, allowing them to process vast amounts of information in parallel. Where a classical bit is either 0 or 1, a qubit may exist in both at once, exploring multiple computational pathways simultaneously. And entanglement allows qubits to share information in ways classical systems cannot replicate. Problems that would take classical computers the age of the universe to solve may become tractable in moments. Quantum computing is still in its infancy, but you can already feel the tremor of possibility beneath it. Cryptography, simulation of molecules, optimization problems, all stand on the edge of transformation. It is humbling to think that the leaps electrons make inside atoms, the same leaps that create colors and light and heat, may one day form the backbone of unimaginable computational power, reshaping science, medicine, and technology. And still, quantum energy reaches even further into daily life, often without our noticing. The LED lights that illuminate homes and streets operate through quantum transitions in semiconductors. The transistors that drive electronics rely on quantum tunneling and quantized energy bands. The fiber optics that carry the world's information use lasers, whose coherence is rooted in quantum rules. Even the chips inside smartphones depend on quantum effects to control electron flow at nanoscales. It is almost comforting, in a way, to realize that the strangeness we once feared has become the foundation of our modern world. Quantum mechanics is no longer confined to laboratories. It hums in power grids, flows through internet cables, guides airplanes, stabilizes clocks, illuminates cities, diagnoses illnesses, and may soon compute the uncomputable. The universe's smallest behaviors, once hidden from human intuition, now shape human civilization. And perhaps, as we step back and take in this sweeping view, we begin to sense that quantum energy is not simply a feature of matter. It is a language that the universe speaks fluently, and that we are only beginning to understand. The more we learn, the more capable we become of crafting technologies that harmonize with these invisible rules. And in doing so, we draw closer to the fundamental rhythms that orchestrate reality. Yet even as these applications dazzle us, another question emerges softly at the edges of our thoughts. If quantum energy governs not only machines but life itself, if biology too is shaped by tunneling, by superposition, by quantum effects woven into cells and molecules, then what does that mean for our understanding of living systems? How deep does quantum influence run within the pulse of life? Is biology simply classical chemistry scaled upward, or does it hum with quantum resonance from within? And so perhaps now, having wandered through the technologies built on quantum principles, we are ready to follow the thread inward again, not to the atom, but to the living organism, to the leaf, to the neuron, to the migratory bird, to the scent molecule, to the subtle ways in which life borrows, bends, and dances with quantum energy. Let us step now toward that next landscape, where biology meets quantum physics, and where life reveals itself to be stranger, more delicate, and more wondrous than we ever imagined. Well, you see, once we recognize how deeply quantum energy shapes our machines and technologies, it becomes almost impossible not to wonder whether life itself might be listening to the same hidden music. And perhaps that is where the story grows even more intimate, more unexpected, because biology, this warm, breathing, evolving tapestry, turns out not to be as classical as we once believed. Beneath the sweeping processes of metabolism and growth lies a realm where electrons tunnel, where energy is transferred with uncanny precision, where molecules sense vibrations in ways that resemble quantum detection, and where creatures navigate the world using mechanisms that seem to borrow directly from the quantum playbook. And that's the thing. The boundary we imagined between the living and the quantum is far more porous than we ever expected. Let us begin with something as gentle and familiar as a leaf catching sunlight. Photosynthesis is perhaps the most important energy conversion process on Earth, and for decades we thought of it as a classical chain of chemical reactions. But when scientists looked closer, they found something astonishing. When light strikes a chlorophyll molecule, it excites an electron, creating what we call an exciton, essentially a packet of energy that must travel through the photosynthetic complex to reach a reaction center. And here is where quantum behavior appears with breathtaking elegance. The exciton does not wander randomly through the molecular maze like a lost traveler. Instead, it explores multiple paths simultaneously, probing the landscape by superposition, allowing the plant to find the most efficient route with near-perfect fidelity. Imagine that. A leaf, quietly performing computations using quantum principles before breakfast. It is almost poetic, I suppose, to realize that the greenness of the world, the foundation of food chains, the oxygen in your lungs, all arise from a process where energy travels by sampling all possibilities at once. A classical system would lose energy as heat, fumbling through the molecular structure. But the quantum coherence observed in photosynthesis allows energy to flow with astonishing efficiency. Life found a way to harness quantum effects long before humans even knew such rules existed. And then there are enzymes, the molecular workhorses of the cell. They accelerate reactions that would otherwise unfold at glacial pace. For a long time, we assumed they worked simply by holding molecules in the right orientation, lowering activation energy, making it easier for reactions to proceed. But deeper study revealed something stranger. Some enzymes appear to use quantum tunneling, allowing protons or electrons to slip through energy barriers rather than climb over them. This tunneling accelerates reactions far beyond classical predictions. The enzyme is not just a passive structure, it is a sculptor of quantum landscapes, shaping the probability fields through which particles move. When you breathe, when you digest, when you think, countless enzymatic reactions rely on these quantum shortcuts. Life is efficient not because it cheats physics, but because it embraces the full breadth of quantum rules. And perhaps that realization invites a moment of quiet reflection. The spark of vitality inside every living cell owes something to particles that refuse to be confined by classical expectations. Yet quantum biology stretches even further into realms that feel almost mystical until we understand the physics beneath them. Consider the sense of smell. For many years, we believed that smell worked like a lock and key. A molecule with a particular shape fits into a receptor, triggering a signal. But certain puzzles challenged this model. Some molecules with identical shapes but different isotopes smell different to humans. This cannot be explained by shape alone. A competing theory suggests that smell may involve quantum vibration detection. Receptors inside the nose may be sensitive to the vibrations of molecular bonds, using a form of inelastic electron tunneling to identify specific energy signatures. In this view, your nose is not simply sensing shapes. It is listening to the quantum music of molecules, detecting how they vibrate. Perhaps that sounds like poetry disguised as science, but in truth, the biology of smell may depend on electrons tunneling through molecules only when the vibrational frequency matches the required energy difference. Your perception of scent, roses, rain, citrus, earth, may be born from quantum resonance. And then, of course, we come to one of the most captivating examples of quantum phenomena in biology: the ability of migratory birds to navigate across continents using the Earth's magnetic field. Classical explanations struggled to account for the extraordinary precision of avian navigation, but quantum biology offers a new perspective. Researchers believe that certain birds possess a light-sensitive molecule in their eyes, cryptochrome, that forms entangled radical pairs when struck by photons. These pairs respond differently to magnetic fields, allowing the bird to sense orientation through subtle changes in chemical reactions. You see, entanglement, That ghostly connection across distance might be whispering to birds as they cross oceans and mountains. Quantum coherence may give them a compass etched not in iron but in probability. It is almost poetic to think that the night sky, the shifting seasons, the great migrations that have unfolded for millennia may be guided by quantum states flickering inside the eyes of birds. And what does this tell us? That life is not merely classical machinery built from predictable chemical parts. It is a delicate dance at the boundary of quantum and classical worlds. Even in our own bodies, processes like vision begin with a quantum event, the absorption of a photon by a retinal molecule, triggering a rapid isomerization that cascades into neural signals. Every sight you have ever perceived began as a quantum transition, a photon collapsing into certainty inside your eye. Perhaps the strangeness becomes even more profound when we consider how fragile quantum states are. They are easily disrupted by heat, by noise, by interactions with the environment. Yet life, which operates at warm temperatures and noisy surroundings, somehow finds ways to maintain coherence just long enough to use it. Nature performs quantum engineering with ease, shaping molecular structures that protect delicate states from decoherence. Life learned to stabilize quantum states before humanity invented the word quantum. And perhaps this invites us to wonder whether evolution, in its deep and silent wisdom, found quantum shortcuts wherever classical physics reached its limits. Not because life needed to reach for exotic rules, but because the quantum world simply is the world. Living systems are built from atoms and electrons that obey quantum laws, and it should not surprise us that evolution found ways to exploit these behaviors. What surprises us is only our own expectation that biology should be classical. Now, as our thoughts settle into the rhythm of this idea, that quantum mechanics pulses through every leaf, every enzyme, every neuron, we begin to feel the edges of another question taking shape. If quantum energy plays a role in life, then what happens when misunderstandings distort these truths? What happens when the language of quantum physics is borrowed, romanticized, or misapplied to ideas that have little to do with the rigorous science beneath them? In recent years, the word quantum has drifted far beyond laboratories and observatories. It has appeared in advertisements, self-help philosophies, and pseudoscientific claims. But the real quantum world is far more beautiful, far more precise, far more demanding than these simplifications suggest. And so, perhaps now that we have seen the true quantum in biology, in photosynthesis, in enzymes, in navigation, in sensation, it is time to confront the misunderstandings that swirl around the idea of quantum energy. Let us step gently, then, into that next landscape, where we distinguish scientific wonder from myth, where we protect the integrity of discovery while acknowledging the allure of speculation. It is time to look closely at the misconceptions that have grown around quantum energy, and to understand why the truth, though less mystical than the myths, is infinitely more miraculous. Well, you see, once we've wandered through the quiet quantum pathways of life, through leaf and enzyme and migratory bird, something almost inevitable begins to happen. We begin to sense how extraordinary the quantum world truly is, how delicate its rules, how exacting its mathematics, and perhaps because of that, the word quantum has, over the years, slipped away from its scientific roots and drifted into conversations where it does not quite belong. You hear it invoked in advertisements, whispered in self-help seminars, stitched into spiritual claims, offered as an explanation for mysteries it was never meant to solve. And that's the thing. The beauty of quantum energy is real, profound, breathtaking even, but it is not magical in the way some imagine. It does not heal through bracelets. It does not bend to belief. It does not respond to intention as though it were conscious. It is far more subtle, far more demanding, and far more astonishing than these misunderstandings allow. Perhaps the most persistent misconception is the idea that quantum energy is some kind of mystical healing force flowing through the body, waiting to be tapped or awakened. The science tells a different story. Quantum energy is simply the energy associated with particles and fields at the smallest scales, governed by well-established physical laws. It is the energy in electrons making quantized leaps,
the energy in photons, the energy in nuclear transitions. These processes are not controllable by thought or emotion, not accessible through charms, crystals, or bracelets. They unfold according to precise mathematical rules that have nothing to do with spirituality or metaphysics, and that disconnection matters because conflating science with belief blurs the boundaries between understanding and wishful thinking. It is tempting to imagine that the strange unpredictability of quantum mechanics, its probabilistic nature, its uncertainty, somehow opens a gateway to supernatural influence. But uncertainty is not
Permissiveness. Probability is not magic. These features reflect the mathematical structure of the microscopic world, not a loophole through which human intention can slip. They do not permit energy to be summoned or transferred by will. They do not allow healing by proximity to an object advertised as being infused with quantum vibrations. There is no scientific evidence, none at all, that such devices or claims have any effect beyond placebo. And perhaps here we should pause for a moment, because the longing behind these beliefs is understandable. Humans crave connection, meaning, and agency in the face of complexity. The quantum world feels mysterious, and mystery invites imagination. But misunderstanding does not do justice to the real quantum universe, which is more intricate and awe-inspiring than any simplified mystical narrative. Another deep misconception is the idea that quantum physics supports certain spiritual or metaphysical claims. But quantum mechanics does not imply that the mind creates reality in a literal sense. It does not say consciousness shapes the universe simply by observing it. The observer effect is not about awareness. It is about interaction. A detector measuring an electron changes its state because the measurement disturbs the system, not because a conscious mind is watching. Quantum measurement requires physical interaction, energy exchange, detection mechanisms, not intention or awareness. And yet, in popular culture, the phrase "you create your own reality" has been given a quantum sheen, as though wave function collapse were waiting patiently for human thoughts to guide it. But that is not how the universe works. The collapse of the wave function occurs through physical processes, not mental ones. The beauty of quantum mechanics lies in its precision, not in its malleability to belief. Perhaps the most poetic misunderstanding is the idea that raising your vibration can alter your state of being in a quantum sense. But vibration, in physics, refers to oscillation, frequency of particles or fields, not emotions or spiritual states. A person cannot raise their vibrational frequency by feeling joy or peace in any literal quantum way. These metaphors can be emotionally resonant, but they are not grounded in science. Quantum vibrations involve specific energy transitions, not subjective experiences. And, there is also the notion that quantum entanglement allows for psychic connection across distances. This misunderstanding arises from a kernel of truth. Entangled particles influence one another's states no matter how far apart they are. But this does not allow information, thought, or emotion to travel instantaneously. Entanglement cannot transmit messages. It cannot be used to sense someone's feelings across the world. It is a correlation, not a communication. The strange connection exists only within the mathematical structure of quantum states. It does not serve as a cosmic telephone line for human experience. We also find claims that diseases can be cured by devices marketed as quantum energy resonators or quantum frequency harmonizers. But the body does not respond to quantum states in that way. Healing is biological, chemical, physiological. Quantum mechanics governs molecules at the fundamental level, yes, but the emergent systems, organs, tissues, immune responses, do not operate through tunable quantum fields accessible by handheld gadgets. Such claims misuse scientific terminology to cloak pseudoscience in a veneer of credibility. And perhaps the most dangerous misunderstanding is the belief that invoking quantum terminology removes the need for evidence. Quantum healing, quantum consciousness, quantum manifestation. These phrases often appear in place of demonstrable mechanisms, but science requires testability, falsifiability, and reproducible evidence. Without these, claims remain beliefs, not knowledge. And belief is not inherently harmful, unless it masks itself as science and leads people to abandon real treatments, real understanding, real inquiry. You see, the universe does not lose its wonder when we remove pseudoscience from it. If anything, the awe deepens. The real quantum world is stranger, more beautiful, more mathematically rich than any mystical reinterpretation. It is a world where particles tunnel through barriers, where atoms leap between energy states, where fields vibrate in ways that shape creation itself. It is a world built on uncertainty, probability, and symmetry. A world where time and energy fluctuate, where vacuum seethes, where entanglement binds particles in a cosmic whisper. And once we appreciate this true strangeness, we begin to see why the myths pale beside it. Mysticism tries to simplify the quantum realm into something accessible, comforting, controllable. Science reveals it to be far more delicate and far more astonishing. And in that revelation, perhaps we find something quietly profound. The universe does not need to be magical to inspire wonder. Its reality is wondrous enough. As we reflect on these misunderstandings, another question slips quietly into view. If quantum energy is so often misinterpreted, how should we think about the future? What breakthroughs lie ahead as we learn to apply quantum principles with more sophistication? Could quantum technologies reshape communication, computing, material science, and energy in ways we have not yet imagined? Could the next century, or perhaps even the decades leading up to 2025 and beyond, bring tools that harness quantum features not as metaphors, but as engineering principles? This is where the next chapter leads us, toward the future of quantum energy, toward quantum networks, quantum computers, new materials, new methods of harnessing energy, new glimpses into the structure of reality. So let us step forward into that unfolding horizon, guided not by myth, but by the true, astonishing potential of the quantum world. Well, you see, once we've cleared away the fog of misunderstanding and allowed the true quantum world to stand in its own quiet brilliance, an entirely new horizon begins to unfold before us. It is a horizon made not of myth or metaphor, but of possibility. The kind of possibility that hums beneath equations and experiments, waiting patiently for human imagination to catch up. And that's the thing. When we ask what the future of quantum energy might look like, we're really asking how deeply we're willing to listen to the universe. Because the quantum world is not only a realm of strange behavior, it is a reservoir of potential, a blueprint for technologies that could reshape civilization in the years to come. Yes, even in the time just beyond 2025, as our understanding deepens step by step. Perhaps the most transformative of these technologies is the quantum computer. Classical computers, no matter how powerful, are bound to bits, 0 or 1, off or on. But a quantum computer uses qubits, which exist in superposition, allowing them to be 0 and 1 simultaneously. It's as though each qubit holds a branching forest of possibilities within it, exploring many computational paths at once. When entangled, qubits share information instantly within a single quantum state, making quantum processors capable of tackling certain problems at speeds unimaginable to classical machines. Simulating complex molecules, breaking cryptographic codes, designing new medicines, these tasks could be revolutionized by quantum computation. But perhaps the deeper revelation is this. Quantum computers force us to see information itself as a physical phenomenon, woven from the same strange rules that govern particles and fields. Computation becomes not a mechanical process, but a dance of probabilities. Yet computing is only one part of the future we glimpse. Quantum networks, sometimes called the future quantum internet, may allow information to be transmitted with perfect security. Not because of clever coding, but because any attempt to intercept quantum data changes the quantum state itself, revealing the intrusion instantly. Communication becomes not just encrypted, but fundamentally protected by the laws of physics. Imagine financial systems, scientific collaborations, even personal messages carried through channels that cannot be hacked without altering the very fabric of the signal. Entanglement may link laboratories across continents, enabling synchronized experiments and new forms of distributed computing. The world shrinks not physically, but informationally, as quantum connections weave an invisible net across the globe. And still, this horizon continues to expand. Quantum teleportation, the transfer of quantum states between distant particles, has already been demonstrated in laboratories. No matter is moved, no object travels, but information about the state is transported instantaneously across space. It is not teleportation in the science fiction sense, but it does hint at a future where quantum states can be transmitted for advanced communication, computation, or sensing technologies. The laws of nature themselves become the communication protocol. Materials science, too, stands on the edge of transformation. Quantum materials, superconductors, topological insulators, exotic phases of matter, could reshape electronics, energy grids, and transportation. Superconductors that work at higher temperatures may allow electricity to flow across cities with no resistance, no loss, no waste. Power grids could become near perfect, eliminating the massive energy losses that occur today during transmission. Magnetically levitated trains, quantum sensors capable of detecting minute gravitational or magnetic variations, ultra-efficient engines. These all emerge from understanding how electrons behave not as particles following classical rules, but as quantum waves moving collectively through materials. Quantum sensing may unlock the world's hidden subtleties. Sensors based on quantum principles can detect gravitational waves, monitor tiny changes in brain activity, locate underground structures, or read Earth's magnetic fields with incredible precision. Even medicine could benefit from quantum-enhanced imaging, allowing doctors to diagnose diseases at much earlier stages by detecting biochemical changes invisible to classical devices. And then there is the dream, still distant, still shimmering, of harnessing quantum energy in new ways. Not in the pseudoscientific sense, but in the rigorous, technological sense, tapping into the quantum behavior of materials to produce cleaner, more efficient energy systems. Understanding zero-point fluctuations, improving nuclear fusion reactions, designing materials that interact with photons in novel ways. These possibilities may open doors to energy technologies that feel almost futuristic. But perhaps the most profound future lies not in machines, but in understanding. As quantum physics advances, we inch closer to unifying the forces of nature, closer to explaining why particles have mass, why space behaves as it does, why the vacuum is never truly empty. We may come to understand dark energy, dark matter, or the deep mathematical structure behind the universe's evolution. Quantum gravity, still elusive, waits like a distant star on the horizon, a theory that may one day merge the large-scale elegance of relativity with the microscopic strangeness of the quantum world. Imagine for a moment a future where quantum theories reveal the true architecture of space-time, where we understand not just the behavior of particles but the origin of the laws themselves, where energy, matter, space, and time become elements of a deeper symmetry, where the universe feels less like a collection of separate parts and more like a single unfolding expression of quantum fields. I suppose it's humbling to consider that every discovery we make pulls us 1 inch closer to answering questions older than civilization. Where does structure come from? Why does anything exist at all? What breathes fire into the equations of physics? And yet, for all its ambition, the future of quantum energy is not a guaranteed path. These technologies require precision, perseverance, and deep humility. Quantum states are fragile. Decoherence lurks at every corner. Scaling up quantum systems is like trying to hold fog in your hands. But this challenge only deepens the beauty of the pursuit. The universe is inviting us to understand it not through force, but through patience, not through domination, but through listening. You know, perhaps that is the quiet lesson the quantum world teaches us, that progress comes from sensitivity, from attunement, from respecting the delicate structures beneath reality. Our future will be shaped not by bending the universe to our will, but by learning the rhythms it has been playing since long before life emerged on Earth. And as we look ahead, toward quantum computers humming softly in cooled chambers, toward entangled networks spanning continents, toward materials shimmering with strange new phases, toward sensors capable of hearing the faintest echoes of creation itself, another question begins to glow gently at the edge of thought. If understanding quantum energy leads us deeper into the structure of reality, then where does this journey end? Or does it end at all? Perhaps every answer opens a new doorway. So let us step now, quietly and with wonder, toward that final reflection, toward the question of what all this means for our place in the universe, and whether by learning to read the smallest vibrations of existence, we might be moving closer to the truth of why the universe is here at all. Well, you see, as we stand at the edge of that unfolding quantum horizon, where future technologies shimmer like constellations just beginning to take shape, there is a quiet moment, almost like a held breath, when the mind drifts back to a simpler, older question, a question older than quantum mechanics, older than Newton, older even than philosophy itself. Because after all the discoveries, after all the equations and breakthroughs and shimmering possibilities, we are left with something profoundly human. What does it all mean? What does quantum energy, in its strange and elegant truth, tell us about the nature of existence, about our place in the cosmos, about the astonishing fact that anything exists at all? And that's the thing. Quantum physics may not offer spiritual answers, yet it illuminates the fabric of reality in a way that invites wonder, humility, and a deep, resonant sense of connection. Quantum energy, as we have followed it through these chapters, is not mystical fuel or cosmic intention. It is the fundamental way the universe organizes motion and structure at the smallest scales. It is the discreteness of photons, the leaps of electrons, the trembling of vacuum fields, the entanglement stretching across vast distances. It is the rulebook beneath matter, energy, space, and time. And in a quiet, almost poetic way, it reveals that reality is not a static sculpture but a living process, a dance of probabilities, a conversation between possibility and form. What makes this so moving, I suppose, is how it reframes our understanding of solidity. We walk through the world believing in tables, trees, bodies, oceans, believing in the firmness of matter. But quantum physics whispers something gentler, almost startling, that solidity is an illusion of scale. At the deepest level, atoms are mostly empty space. Electrons are clouds of probability. Energy is quantized. The vacuum itself seethes with motion, and matter persists not because it is rigid, but because uncertainty stabilizes it. Existence is woven from fluctuations, not from permanence. There is something humbling in that. The world we know rests on foundations more fragile and intricate than we ever imagined. Every breath, every heartbeat, every unnoticed moment is built from quantum processes happening ceaselessly beneath awareness. You and I, we are arrangements of vibrating fields, patterns of energy shaped by probability. We are not separate from the quantum world. We are quantum phenomena scaled up into consciousness. And when you let that idea settle, gently, it almost feels as though the universe is inviting us to reconsider what it means to be alive, not in a mystical sense, but in a deeply physical one. We are part of a cosmos that is fundamentally dynamic, relational, probabilistic. A cosmos where unpredictability is not a flaw, but a feature that allows complexity. A cosmos where particles can be connected across unimaginable distances, where time itself trembles, where emptiness is never truly empty. Perhaps that is why quantum physics often feels philosophical, even when its mathematics is rigorous and unforgiving. It confronts us with truths that defy intuition, truths that blur the line between what is possible and what is real. It reminds us that certainty is a comfort of the macroscopic world, not an inherent property of the universe. It tells us that the future is open, shaped not by predetermined paths, but by fields of probability, constantly collapsing into outcomes. You see, When early physicists first encountered quantum phenomena, many described the feeling as being pulled into a deeper reality, one that was shimmering just beneath the familiar one. They did not abandon science. They did not drift into mysticism, but they recognized that the universe was more subtle, more intricate, more astonishing than classical physics had ever hinted. And in that subtlety, there was beauty. A quiet beauty, born not from certainty, but from structure, not from simplicity, but from complexity. And perhaps that beauty gives rise to another thought. If the smallest scales of reality are shaped by chance and probability, then life itself becomes a story etched into a canvas of quantum fluctuations. The formation of stars, the synthesis of elements, the emergence of molecules, the spark of biology, all of it unfolds within a universe alive with trembling fields and quantum possibility. We are children of quantum events. Our atoms were forged in stars by nuclear transitions. Our vision begins with photons collapsing into molecules in our eyes. Our memories depend on electrons tunneling through proteins. Our intuition, creativity, consciousness itself, emergent from networks built from quantum components. It is humbling to realize that the universe, in all its vastness, is not indifferent. It is participatory. Not because it listens or responds to intention, but because the rules that sculpt it require interaction, measurement, exchange. Reality unfolds through relationships, particles with particles, fields with fields, observers with observed. It is a cosmos stitched together by encounters. And the more closely we listen to these ideas, the more they soften the boundaries between science and meaning. Not by blending them, but by showing that wonder belongs to both. Quantum mechanics does not explain purpose, but it enriches our understanding of reality. It does not tell us why the universe exists, but it offers glimpses of how. It does not diminish mystery, it deepens it. Because every answer reveals a deeper layer of questions. Even the question of the universe's origin becomes richer through quantum insight. The cosmic microwave background is filled with fluctuations that began as quantum tremors in the earliest moments of space and time. Galaxies, clusters, filaments, all emerged from quantum seeds amplified by cosmic expansion. Without quantum uncertainty, the universe might have remained a uniform mist. Instead, structure formed, stars ignited, life became possible. Uncertainty, at the beginning of time, sowed the asymmetries that would one day become us. And as we look ahead toward the future we explored in the previous chapter, we recognize that quantum energy will not only reshape technology, it will reshape perspective. Quantum computers may give us new ways of thinking about computation and logic. Quantum networks may redefine communication. Quantum materials may alter how we harvest and use energy. But perhaps the most profound change will occur not in our devices, but in our understanding. As we learn more about the quantum world, we are forced to rethink identity, connection, causality, space, time, these fundamental pillars of comprehension. I suppose that is where the quiet philosophical resonance of quantum physics comes from. The more we learn, the more the universe appears not as a clockwork machine, but as a creative unfolding. The more we measure, the more we realize how much remains unmeasured. And the more deeply we understand the rules, the more astonishing their implications become. And yet, for all this wonder, there remains one final lingering question. A question that threads itself through every chapter, every idea, every trembling field beneath reality. If quantum energy is the foundation of everything, of matter, of motion, of life, of thought, then what lies beneath quantum energy? What lies beneath the rules themselves? What is the deeper truth, the deeper structure, the deeper origin of the universe? It is here at this threshold that our journey begins to turn inward once more, not toward machines or atoms or birds or stars, but toward meaning itself. Because once we have followed quantum energy through physics, biology, technology, and philosophy, we arrive at a final reflection, one that asks not how the universe works, but what it means for us to be part of it. So let us step, gently and with curiosity, toward that closing contemplation, toward the question of whether, by understanding the smallest vibrations of existence, we might be approaching the heart of the universe's deeper truth. Well, you see, after journeying through these shimmering layers of the quantum world, through particles and fields and trembling vacuums, through the strange grammar of probability and the delicate architectures of life, there comes a moment when the mind, almost on its own, begins to lean back and take in the whole landscape at once. It is like standing on a ridge after a long ascent, watching the valleys of understanding stretch out behind you, each one carved by questions older than language. And perhaps this is where the quiet truth begins to reveal itself. Quantum energy is not merely a chapter in physics, nor a niche of mathematics, nor an exotic subset of scientific curiosity. It is the foundation, the pulse beneath matter, the blueprint of every rhythm the universe has ever learned to play. You know, for so long we imagined the world as a mechanical place, solid, predictable, governed by certainty. But the quantum world whispers something softer, almost tender, if we dare to listen. It tells us that reality is layered, that beneath the solidity of wood and stone and flesh lies a restless ocean of movement, of fluctuations and leaps, of sudden transitions and drifting waves. It tells us that the universe at its root is not rigid but alive with possibility, and that perhaps is the quiet miracle. Because without that possibility, without those quivering uncertainties, nothing complex could have formed, no star, no planet, no leaf, no mind pondering its place in the cosmos. As we reflect on all we have explored, light cascading from the sun as packets of energy, electrons leaping across quantized steps, atoms forming from vibrating fields, life borrowing quantum strategies to survive, there is something deeply humbling in seeing ourselves as part of this unfolding process. We are not separate from the quantum world. We are woven from it. Every breath, every thought, every memory arises from interactions that began billions of years ago in the trembling womb of the early universe. And that connection, so intimate and so vast, invites a kind of reverence. Well, perhaps reverence is the right word. Not a mystical reverence, not one built on myth or misinterpretation, but a reverence born of understanding, of realizing that the smallest fluctuations in the vacuum gave rise to galaxies, that the uncertainty of particles seeded the asymmetries that eventually became stars and planets, that the quantum rules governing electrons eventually led to chemistry, and chemistry to biology, and biology to consciousness. It is astonishing, isn't it, to think that uncertainty itself helped shape the world we know. That randomness, constrained by elegant mathematics, sculpted the architecture of existence? And that's the thing. The more deeply we look into quantum energy, the more the universe begins to look less like a cold machine and more like a story, one written in a language of waves and probabilities, of symmetries and broken symmetries, of leaps and collapses and fleeting possibilities that either fade or crystallize into form. A story unfolding not once but constantly, at every moment, in every place where particles interact and fields overlap. A story told on scales too small for the eye, yet too vast for the mind to fully grasp. You see, when we peel back the layers of existence, something quietly profound emerges. The universe does not simply contain quantum processes. It is a quantum process. Every structure we see, every planet orbiting its star, every star orbiting the center of its galaxy, every galaxy drifting through space-time, ultimately rests on rules playing out in the invisible depths. The macroscopic world, with all its stability, its durability, its comforting predictability, is built upon the flickering unpredictability of the quantum domain. Classical reality is the averaged-out glow of quantum shadows, and perhaps, in a way, this gives us a new sense of meaning. Not the meaning imposed from outside, not the meaning written into sacred texts or engraved into myth, but the meaning that arises from understanding, the meaning of belonging. because the fact that we can study the universe at all, that we can follow particles through equations, that we can detect the faint signature of photons born billions of years ago, that we can unravel the structure of atoms and nuclei and living cells, suggests something extraordinary. It suggests that the universe has given rise to something capable of reflecting on it. The cosmos becomes conscious of itself through us. That is not mysticism. It is simple consequence. The atoms in our bodies were forged in the cores of stars. The photons that strike our retinas flowed from nuclear reactions governed by quantum fusion. The neurons firing in our brains rely on ion channels and proteins shaped by quantum chemistry. And the curiosity that pushes us to explore, to question, to wonder, well, perhaps that too is rooted in the restless, open-ended nature of the quantum world, where possibility never fully collapses until it meets the conditions to do so. And as we linger here, at the edge of this long exploration, I suppose a quiet question rises like dawn over the landscape. Why is the universe built this way? Why must energy come in quanta? Why must uncertainty rule the smallest scales? Why must particles behave like waves and waves like particles? Why must the vacuum tremble instead of rest? Why must the very fabric of reality refuse to be simple? Perhaps the answer is simply that a universe built any other way would not have been interesting, or stable, or creative, or alive. A completely deterministic universe might have been predictable, but barren. A universe without quantum rules might never have formed structure. A universe without fluctuations might never have escaped perfect symmetry. What we perceive as strange or counterintuitive may be precisely what allows the cosmos to bloom. And perhaps that is the hidden gift quantum energy offers us. Not control, not mysticism, not shortcuts, but perspective. A chance to see the universe not as something separate from us, but as a continuous unfolding in which we participate. A reminder that certainty is not the foundation of reality, but curiosity might be the closest thing we have to navigating it. A recognition that even the smallest tremors of existence matter in ways we rarely consider. You know, there is a soft beauty in that. The idea that the universe is not a solved equation, but an invitation, not a fixed script, but a field of possibility, and that our role, humble as it may be, is to listen, to observe, to wonder, to learn. And if there is one final thread that ties all of this together, it is the feeling that understanding quantum energy has brought us closer, not to answers, but to questions worth asking. Because the deeper we go, the more the universe seems to whisper, there is more. Beneath every phenomenon lies something smaller, something stranger, something waiting to be seen, which leads us gently to the threshold of yet another journey. If quantum energy reveals the structure beneath matter, then what reveals the structure beneath space and time themselves? If uncertainty shapes particles, what shapes the uncertainty? And if the universe is a tapestry woven from vibrating fields, what loom holds those fields in place? So let us take one final breath together before moving on, feeling the weight and wonder of all we've uncovered. And then, when you're ready, we will step forward into a new question. What lies beneath even the quantum world? And how close might we be, in this strange era just beyond 2025, to glimpsing the deepest architecture of reality itself?